everyone, this is Vijetha, Associate Professor in the Department of ECA, MLR Institute of Technology. Today, I would like to have a talk on second part of language construction conventions from linear and digital integrated circuits. Previously, we have discussed 6 language construction conventions. The other language construction and conventions are logic values, strings, data types, scalar and vectors, parameters, and operators. So, where we'll be using these logic values, strings, and data types, and what are the purpose of using these language construction conventions, we'll see in the next slides. Logic values. Here, we can use 4 logical values. Those are 1, 0, x, z. 1 signifies the level 1, or we can say the true level, or we can say the higher state. And 0 signifies the 0 or false state, or you can say the lowest state, that is approximately 0. And x and z determines the indeterminate state, and z represents the high impedance states. So the same thing I have explained here. 1 signifies the 1 or high or true level, where 0 signifies the value of 0 or lower state or false state. Other than this 1 and 0, you have 2 more logical values. Those are x and z. X represents the unknown or uninitialized values, which you can also say it as a don't care conditions, don't care cases. That is, we don't know whether it is 0 or 1, maybe 0 or maybe 1. And Z represents a high impedance state. Z represents high impedance states. These are the 4 logical values which are used in the digital circuits. Here, Verilog is a high-level programming language which can be written to execute the digital circuits. So, in digital circuits, we'll be using a 4 logical values which are 1, 0, x, and z. The next one is strings. See, always it's not possible to show the logical levels. So, these always it's not possible to show the logical levels with 0, 1, or x or z. See, these logical levels can also be associated with the strings in digital circuits. Okay. So, multiple assessments are often combined to reduce the silicon area or to reduce the pin out. To facilitate this, we can assign the strength to a logical levels. Instead of, see, when you are talking with respect to a circuit level designing, when you're talking with the circuit level designing. For example, if you have taken a NOT gate, I'm taking a CMOS NOT gate. The CMOS NOT gate can be represented in terms of PMOS and NMOS as shown here. This is an output and this is an input. See, for simple NOT gate, if you want to write the Verilog code, we used to have a primitives. And those primitives can be called here simply like NOT of output comma input. Or you can also use a assign structure, assign O is equals to complement of I. So you can either use a primitive or you can use the assign structure in data flow. But here in circuit level designing, when you want to represent the VDD or you want to represent the ground or you want to represent the flow of this transistor switching on and on levels can be represented by using this strings. It's not possible to use always zeros and ones to represent the logic level. It may also use these strings to represent the flow of the power signals. So, generally, Verilog has 8 strength levels. In that, 4 of them are used to drive the types and Three of them are used to drive the capacitive types and one is used to represent the high impedance type. We'll see step by step in the next slide. Okay. When a signal line is driven simultaneously from two sources, the strength level, whatever the strength level is stronger, that will be considered. When a signal line is driven simultaneously from two sources of different strength levels, the stronger of the two prevails. For example, if two signals are given to a module, let us say that this is strong 0 and let us say this weak 0. So it can drive strong 0 and weak 0 as an inputs to a module. But as the strength of the strong 0 is more comparing with the weak 0, it pulls the strong 0 as an output to this module. That is the thing which have been explained. If two sources of different strength levels, the stronger one will be prevailed. Stronger one will be accepted. How do you know the strength levels? We'll see in the next slide. What are the strengths and what are the levels of the strengths can be seen here. So as we have discussed just now, as we are having 8 different strengths starting from 0 to 7, the first highest strength is supply drive. We also discussed that the 3 are of drive type and 4 of them are capacitor type and 1 is of high impedance type. The three drive types are supply drive, strong drive, pull drive. In that, strong drive is having a highest strength and which can be given with the keyword called supply 1 and supply 0, and abbreviation for this is given with SU1 and SU0, which can be used to represent the power supply connections in your circuit. For example, here in the circuit, the supply pins are VDD and ground. So here you can give this as a strong 1 and here you can give this as a strong 0. Okay, so this supply, instead of the strong you can give the supply 1 and supply 0. The supply 1 represents the VDD, which is having a highest strength comparing with the supply 0, which represents a ground here. So here the first highest strength is supply drive, which is given with the supply 1 and supply 0 and which can be used to connect the power supply connections. The second drive strength is strong drive, which has given with the strength value of 6 and the keyword available for representing a strong drive is strong 1 and strong 0, which can be used to assign the output strength or for a default gates. To assign the output strengths and also it can be used to assign the default gates. The next one is pull drive, which is given with the next highest level to a strong drive, and the keywords here are pull 1 and pull 0, which are used to assign the output strength as well as for the gates. And the next one is large capacitance, which is given with the strength level of 4 and the keywords are given with large 1 and large 0, which is used to represent the size of a tri-register. Next one is weak drive, which is given with the strength 3 and the keyword is given as weak 1 and weak 0, and which is also used to assign the output strength and to assign the gate levels. And the other one is medium capacitance, which is given with the strength 2 and the keywords are medium 1 and medium 0, the same thing which is used to represent the size of tri-register. Similarly, like capacitor, small capacitor also used to represent the size of a tri-register. And the next highest one is high impedance, which is used to represent the tri-stated lines. Here, for example, if I have a module which is having a 2 strengths, which is given with the supply 1 for VDD. Let us assume that supply 1 is for VDD and the strong 0 is given with the ground. So as this is having a highest strength, it drives the supply 1 to the input of your module. And here these three are driving capacitance. So the circuit takes a supply 1 as an input. It drives the supply 1 as an input to the module. Next, few examples are illustrated here. If the signal line A is driven with the two sources, a few examples are considered here. If a signal line A is driven by two sources, B at level 1 with a strong 0, let us assume this as A, which is having a B, and C. B is at first level, which is given with the strong 1, and C is given with the pull 0. So this A value will take strong 1 as its input. It drives the strong 1 as its input because the strength of strong 1 is higher than the pull 1. Another example, if a signal line A is driven by the two sources, B with the pull 1, B with the pull 1, and C at the strong 0. So here, pull 1, strong 0. This strong 0 is having a highest strength comparing with the pull 1, so it takes a value of 0. Next, similarly, if a signal line is driven by two sources, B with the strong 1, say B with the strong 1, and C with the strong 0. Here the strong 0 and strong 1 are given with the same strengths. So it reacts as an indeterminate state because the strong 0 and strong 1 represents the same strength levels. Next, here, if a signal line is driven by two sources, one with the weak 1, C with the large 0. Weak 1, large 0. This is weak 1 and large 0. So the larger capacitance is having a higher strength. So it takes large 0 as a input. So it will take a value 0 as the input to the source. Input to the A. A is 0 will be the source to the A. So these are the few examples which can be discussed to understand the strengths. Next, coming to the other construct and convention, which is data type. Here, there are two different types of data types. Net data type, variable data types. See, these data types of each variables or signal has to be declared prior to its use. If I am taking a number, if I have not defined that number either as an integer or real number, then the program cannot take it as a float value. It takes it as a normal integer. Data type of each variable or signal has to be declared prior to its use. For example, when you are writing a C program, if you have not defined the integer value or a float value to your number, it doesn't consider whether it has to take an integer value or a float value. Similarly, here you need to specify the variables, either it is a net type or it is a variable type. So basically, data types are having two different concepts. The first one is nets. What is net? Net signifies a connection from one circuit unit to other such that net carries the value of signal it is connected to and transmits to the circuit blocks connected to it. If the driving end of net is left floating, the net goes to a high impedance state. If it is not connected properly, then it takes input as a high impedance state. The other one is, there are two different types of nets. One is wire and the other is tri. So what is the difference between wire and tri? See, wire is a simple interconnection between the two blocks. Only one output is connected to a wire and is driven by that. Whereas tri is a signal line as a wire but can drive more than one signal output. So let us assume that I have a block 1 and the output of block 1 has to be transmitted to block 2. And the inputs of blocks are, let us assume, A and B, and output of this block is O. So this is a main block which is having inputs A, B and output O. Here, a single output of the module 1 has to be transmitted to the module 2. In this case, you can use a wire. It's just an interconnection between two elements and it can drive a single value. Whereas a tri is also an interconnection between the module, but it can drive more than one signal output. So if you want to drive 2 or 3 inputs to module 2 from module 1, in this case, you can go with the tri. The function of wire and tri are same, which are used to interconnect the two different elements. But if you want to drive a single output, then you can go with the wire, or if you want to drive multiple outputs to a second module, then you need to use a tri. The next one is variable data type. Is an abstraction for storage device. It can be declared to a keyword called register and stores the value either 0 or 1 or X or Z. Net or wire connected to a register takes on values stored in the register and can be used as an input to other circuit. But the output of the circuit cannot be connected to the register. In Verilog, we'll be writing a design description. And this design description can be called to a test bench code where you can execute your design description in the test bench code. Here in design description, we'll just declare what are the inputs, what are the outputs, and what is the function of your program. And this program can be called to a test bench to execute here. So here, you need to give the inputs to the variables. So if you want to give the inputs to the variables, the input values has to be stored into the variable. And this storage can be done by using this data type by declaring it as a register A is equal A or register B. If you declare this variables with the register, you can store the values to A and B, or else you can't store the values in A and B. And your output, let us assume that O is an output. And here for your output, you should not declare with the REG here. The values which are giving as inputs to your design description can be given with the keyword called REG, but not to the outputs of your design description. The value stored in the register is changed through a fresh assignment in the program. Some examples are time, integers, real and real times, or some examples which we can use here to declare the data types. Coming to a other one, which is scalars and vector. A single bit can be stored or changed or transferred is said to be as a scalar. If you are talking with a single bit, then you can give a scalar. For example, NOT gate, which is having a single input, and let us assume that which is having a single output. So this can be treated as a scalar. And coming to vector. Here, I'm using a module and I'm using a of 0 or 2 inputs for AND gate, 2 inputs for OR gate, 1 input for NOT gate, and 2 other inputs for NAND gate. Here, Instead of representing A, B or A, B repeatedly, I can use this A as a vector form as A of 3 is to 0. So, A of 3 will be given as an input to a one AND gate. A of 2 can be given as other input for OR gate. A of 1 is given as an input for NOT gate, and A of 0 can be given as the other input to a AND gate. So if you want to define a single variable for M to drive n inputs, you can go with the vector form. This is just an example. Like that you can use to represent a bus, to represent the address bus, or to represent some variables, etc. Here I have shown one example. Let us assume this is circuit 1, this is circuit 2, which has a 4 binary bits as a data, which is transmitting from circuit 1 to circuit 2. If the read pin is enabled, then circuit 1 reads, circuit 2 reads the data from the circuit 1. If write pin is 1, then you can change the data in the circuit 1. Okay. So here the data which I am presenting in terms of B of 0, B of 1, B of 2, B of 3 is a vector representation, whereas read pin and write pins are represented as a scalar, whereas WR and read are represented as a scalar. So here you can transmit either 1 or 0. Here you can transmit 4 bits at a time. 4 bits at a time. You can transmit 4 bits at a time. So this is scalar and vector. Few examples are given. Here wire 3 to 0 A. See here A is a 4-bit vector. Wire and trie are of net type. Just we have discussed wire and trie are the keywords which are used to declare a net type. And the bits are represented as, see, first they will be constrained from here. This is A of 3, A of 2, A of 1, A of 0 will be assigned. And register, which is a register type, and it is representing with the 2, 1, 0, this 3 bits. It is a representation of 3 bits, which is of a register type, and the bits are stored as B of 2, B of 1 and B of 0. Similarly, register 4 is to 2, that is, it's a 4, 3, 2, 1. Again, it's a 3-bit vector, the same register type, and the variable has been assigned with the C. See, from B of 2 to B of 1, and here it is from C of 4 to C of 2. Here, wire -2 to -2 to 2. D, that is -2, 1, 0, 1, 2. 5-bit vector. Individual bits are defined with D of -2, D of -1, D of 0, and D of 1 and D of 2. Wire is also a net data type. Here, this wire or this wires will not store a bit, but the register will store a single bit, either 0 or 1. If you are representing this as a vector, then based on the vector size, the number of bits can be stored. Here 3 bits can be stored. 2, 1, 0. 3 bits can be stored in a B. Here also 3 bits can be stored in a C. And how to, okay. Next, parameters. In some designs, parameter values are not decided. In some designs, certain parameter values are not decided at the outset. See, for example, when you are deciding with the bus weight, or when you are deciding with respect, when you are doing a program with respect to memory, the memory size may not be fixed. At the end of your program, you want to use a little bit more memory, then you need to change the size of your memory, or you need to expand the size of your memory. So in that case, you can use as parameters, not only for memory. Just I have taken the example of memory, but you can change the bus width, you can change the lasting first out depth, and you can change the memory size can be decided. These can be decided at the later states. Not only this, and there are some other examples also. Okay, in some designs, certain parameter values are not decided at the outset. Proportionality constant, frequency scaling levels, number of taps in digital filters are some examples here. So these examples have some situations where the size of design is left open. In some cases, your design should be kept open. The size of your data can be kept open. So those examples are bus width, LIFO depth, memory size, or some parameters which can be decided at the end of your program. All such constants can be declared as a parameters at the outset in a Verilog, and the values can be assigned to them. For example, as I said, see, I have taken a memory elements 0 to 10 values. 0 to 10 values. But at the end, I want to add more 10 variables here, or I want to increase my storage length. Then what I will do? I will left open this parameter, and the size of the parameter can be decided while you are writing the program. So you need to use a keyword called parameter to resize your bus width or LIFO depth or memory size. For example, parameter the word size 16 and parameter word size 16 and memory size is 256. So it is going to be arranging 16 bits in a 16 rows. The first one just defines the 16 bits. That is, just 16 bits have been defined with the parameter. And here the parameter word size is 16 and the number of rows are also 16. So total memory size will be 256. Such parameter assignments are made at the compiler time. Parameter values cannot be changed at a runtime. However, parameter has been assigned a value in a module definition can have its value change at runtime. That is, when the module used at runtime in some other design or when it is tested. Such modifications are carried out through a DEF parameter statement. Generally, these values, when you are declaring with a keyword called parameter, these values cannot be changed at runtime. But in some certain cases, you can change. That is, when you are assigning some parameter values in your module, those parameter values can be changed at the runtime or at the testing time by using a keyword called def parameter. So here you can change the values at runtime or you can change the values in your test code operators. See here also we have 3 operators: unary, binary and ternary. Unary operators is associated with a single operand. Example is NOT GET. And binary operator associated with the 2 operands, whereas ternary is associated with the 3 operands. Okay. For example, they have given this as a binary and ternary examples. I will show here different types of operators. Unary operators. See, these are the unary operators which are having a highest precedence. Next, multiplication, division, modules are the next highest precedence. Next, addition, subtraction will be having a highest precedence. It is lower than the multiplication, division, modulus, but higher than the remaining things. There are shift operators, left shift, right shift. Relational operators, left shift, right shift. Sorry, relational operators. Equality operators, inequality, equality operators, and reduction operators. And these are the logical operators, and this is the conditional operators, which is called as a ternary operator, which is called as a ternary operator. If you are using only a single operand, then it is called as a unary operators. If you are using a two operands, then it's called as a binary operands. If you are using a three operands, then it is called as a ternary operators. This is a case we can see which is having a highest precedence. So here we have discussed about a tri-wire which are of net type, and register is a variable type. These are the data types. Next, we have read with the strengths which can be used in circuit level designing. We know what is the highest strength precedence and what is having a lower strength precedence. We have seen the keywords for this strengths as well as the precedence of this strengths. And the next one we have checked is parameter. Parameter keyword is used to change the values, not exactly values, change the size of your memory, change size of the memory, or to change the size of bus. And you can also use def parameter keyword to change the size of the memory and bus at the runtime, where this keyword cannot be used at the runtime. To change this size and size of bus, this parameter cannot be used at the runtime. If you want to change the size of your memory or size of the bus, you can use the def parameters. And we also know that we have four logic values which are 0, 1, X and Z. High impedance state, indeterminate state, 0 and 1. So these are the few topics which I have discussed in this video. Thank you.